Hi there, this is Thomas Clausen from investmentexcel.com. I will speak today this presentation about modified duration on simple cash flows and on one particular bond. We will look at the formulas underlying the modified duration measure. We look at present value and yield to maturity, both concepts underlying the application of the measure. This video and the Excel workbook are both available on investmentexcel.com and spotafile.com. Okay, let's kick off by just looking at the simple formulas. Remember, the Macaulay duration is a time weighted relative present value measure on all cash flows, and the modified duration is simply the Macaulay duration standardized by 1 plus R. So that gives us a totally new measure, at least in terms of interpretation, because now with the modified duration we can visualize or calculate what happens with the present value of the bond given an absolute shock to the yield to maturity of the bond, not a relative shock on the interest rate. And that makes, of course, the modified duration measure much more easily applicable. Moreover, the modified duration measure can be approximated by this formula, that is, the continuous interpretation of the derivatives can be transformed to discrete transformation using the delta. And that turns out to be very interesting, because an approximated change in return of the cash flow of the bond on the left side here is measured by the modified duration times the change in interest rate. Alright, we will see about this a little later. Let's just start by calculating the Macaulay duration of this simple cash flow structure. 5 years, equally spaced, $1,000 expected to be paid to investor in one on each time. We discount, as usual, all expected cash flows, and when we work with duration measures, it's always by the yield to maturity. And here I have assumed a 3% yearly yield to maturity. That is, the 5-year yield to maturity is 3% on the interest rate curve. So here are the discount factors, and here are the corresponding present values for each J cash flow. So this one on year 5 is discounted the most, so 1,000 times the discount factor. And what we need to calculate the Macaulay duration is the relative PV weight of each PV on the time periods. So here we calculate the PV, which is here, divided by the total PV. So 862 divided by 4,500. And with those weights we can now calculate the Macaulay duration as the sum of the time multiplied factors. So here, for instance, on year 5, we calculate 5 years with the weight of 5 years. And it gives us 2.95 as a Macaulay duration. And as I said, in order to achieve the modified duration, we need to scale it by 1 over 1 plus R. And this is done over here. So I have the original 2.941. And I simply divide it by 1 plus yield to maturity, the 3%. That gives us a modified duration of 2.86. And that's it. That's the duration measure. And of course you can note that the modified duration measure is always lower than the Macaulay duration. But they have two very, very different interpretations. Macaulay duration is in years or in periods, and the other one is in percentage. So the modified duration is actually 2.86% and the other one is 2.95 years. This one, Macaulay, it's a break-even level. This one is a percentage, an expected percentage shock of 1% of interest rate change. And let's see that. If you look at the present value before a shock, we discount it by 3%. So this is the original present value of the cash flows. That gives us this one. And if we shock the curve or the yield to maturity by 1% upwards on all maturities, we will end up with a lower value, which is calculated down here, where we price the cash flows on a higher yield to maturity curve. The theoretical PV change of the cash flow, or the bond, if we assume it's a bond, it's minus 2.79. So this one divided by this one, minus 1. That's the theoretically correct price change given a 1% change upwards in the interest rate. That cannot be discussed. But it turns out that modified duration approximates this correct change quite good, as we see here, minus 2.856. So we simply use this formula minus the modified duration times 0.01. But it's not exactly the same, and that's because of the approximation, because we are working now with non-infinitesimal changes. And as we will see in later presentations about convexity, much of it can be captured by another adjustment, approximation adjustment called this convexity. Alright, that's the bond duration, Macaulay and modified. Let's look at the bond. I have found a 25-year long bullet bond, a Danish bond, issued by the Danish state. And I would like to replicate with the formulas laid out in the previous sheet the calculation that Bloomberg makes of modified duration and the duration, and we see them here. So let's see if we can replicate these calculations. But first we have to make sure that the yield to maturity exactly the same in our cash flow as it is on the bond. And we see here that the yield implied in this bond, given the spot price and the accrued interest, is 1%. So if I didn't have that, I could calculate it in the usual way by trial and error. So adjusting our cash flow to the cash flow or to the present value given by the market price and the accrued interest. So we have the spot price observed in the market, the accrued interest. That gives us a total price that the investor has to pay for the bond. And here we calculate our cash flow structure, and exactly with a discount rate of 1%, it's the same. So based on this, we should be able to calculate the Macaulay duration and also the modified duration. And we do what we always do. We find the total cash flow on each time period. I have laid them out here. Sum of coupon and sum of repayment. And as it is a bullet bond, there will be no repayment until the last maturity date. Present value each time calculated here. Taking the sum of this, we will get the cumulative price here. And as we did in the previous sheet, we find the relative PV values on each time period, each cash flow. So first one, take the PV of the first 4.5 US dollars or Danish kroner as it is, it's a Danish bond, and divide it by the total price up here. So we do that all the way. Clearly it sums to 100%. We scale it by the time, and that will give us the final Macaulay duration. So over here I have the sum of all the relative weighted times. Modified duration, again, scale it by 1/1 plus the yield to maturity implied in the bond price. So we take Macaulay duration divided by 1 plus the YTM at 1%. So let's see. The Bloomberg calculation give us 17.27 and 17.10. So it should be correct. Normally there can be some slight changes between the Bloomberg price and the price that you calculate yourself, because Bloomberg has exact dates on all cash flows, that is including weekdays and holidays and so on. And let's just, as we did in the last sheet as well, let's look at the approximation strength of the modified duration measure. Today we have this present value of the bond, and let's shock it. Interest rate goes up by 1%, and we get a massive drop in bond price, in the theoretical bond price. If we, on the other hand, change it downwards by 1 percentage point, that is, we discount at 0, we get a massive increase in bond price. Note that, of course, when we discount by 0% as YTM, it's just the sum of all cash flows. So the sum of all coupons until maturity plus the principal. This corresponds theoretically in the interest rate up scenario to a drop in -15%, and if interest rates go down by 1% assumed, the bond price will go up by 19%. So this one just being this one divided by the present value, and this one being the new value after change downwards divided by the present value. Okay, what does that say? It says that the modified duration captures not all of the change. So using the formula from the previous sheet, if interest rate goes down by 1%, by the modified duration approximation, the bond should increase by 17.10%. It goes up by 19, so it underestimates, the modified duration underestimates on the upside, and also good for the investor. When interest rate goes up, it tells the duration measure, modified duration measure, tells that the bond price would go down by 17.10%, but it only goes down by -15.39%. So on the upside, it underestimates the value for the bond investor, and on the downside, it underestimates. So both scenarios good for the long position, the investor holding the bond. Obviously not for the one shorting the bond or the borrower. And we will see later that this difference is due to what we could call, or what is called, convexity. Alright, that should be it for now, and this sheet is flexible in terms of changing all inputs for various bonds in the US market, in the European market, and so on, with different coupons, different compounding rates, different cash flow structures, bullet, serial, annuity, and so on. So it's just changing all these, and you'll get a full calculation table. Thank you.